Okay, yeah. Shit. Well,
Good morning.
it's better, but it's not great. Okay, see you, man. See you.
David, your mic is on.
Hi, all.
Good morning.
Yeah, Christina, we did. It wasn't all three of us, Nick and Selman and I. Yeah, we did do a grading marathon. As I was grading, I was thinking I actually prefer cleaning the basement to grading. But I know it's hard to generate. I'm not going to generate a lot of sympathy from all of you about how unpleasant it is for me to grade exams. People did, well, I'll wait until more people are here before I talk about the exam at all. Yeah, no, yeah, Dan, I'm not sure. I actually feel like, oh, wait, I don't have the volume on. I can't hear any of you. Yeah, no, when I'm cleaning there is no activity when I think, I'd actually rather be grading exams. Although sometimes, I mean, there are positive things when someone's, does well, then that's nice. But all in all, it is a soul sucking activity. Um, yeah, no, the neighbor's house without heat, that wasn't so bad. It was more the smell of the Hallmark store type candles that was a little overwhelming. But um, yes, Eric, I can acknowledge that could be. Um, yeah. Shoot, I was going to say something clever and I forgot. I'll just shoot. There's something I want to say. We'll wait another minute
Well,
for
Doc, tell
people.
us the news. How bad was it?
Hmm?
Well, Doc, tell us the news. How bad was it?
Yeah, so I mean, it, I don't know I have not looked at the distributions at all. Like how many people were in what range, just because didn't get them done until late last night. So I don't know anything about like grade scales or, you know, I do know I don't know, there were half a dozen scores that were below 10 out of 80, 7 or 8 scores like that. And then there were maybe 7 or 8, no, maybe 8 or 10 scores that were basically 100 or within a point of 100. And so pretty much everything in between. So they kind of looked, who did what questions in grading. I think I did 2 and 4. And I don't know who, I forget. Selman did one of 1 and 3, and Nick did the other. I don't know who did which. Um, okay. Yeah, no, there's no second exam for this. Farhan. Yeah, I mean, I think people sort of did okay on this one. That's, so in 2020 well, I graded 2 and 4 because they were the shorter ones. So we try to divide the grading evenly, but well, you can do the arithmetic with 4 problems and 3 people. Um, so yeah, so Gregory, I don't want to say like what okay is for now. And no, there's no scale yet because I haven't even looked at how many people did where, and I haven't compared the problems to problems from other years or other colleagues from other
It's
schools.
as if
So
the weight of the world rests upon this.
the what?
It's as if the weight of the world rests upon this.
Yeah, exactly. So we'll figure it out. All right. So I assume people oh wait, shoot, I have to get one prop. I'll be right back. For some of what we're doing, we need a cylinder and circles. And so this may look like an ordinary kitchen jar, but it's actually a highly technical piece of educational material. Okay. Yeah, it does sound that way, Dan. It isn't, though. All right. So I'm going to assume people watched the video between Tuesday and now. And we'll review a little bit, but we do have to sort of go forward. So, right, so chapter 12 is really on chapter 12 in the open source book on Faraday's law. Oh yeah, Dan, yeah, in the video. Yeah, last year. That was I was convinced my kids were watching something, streaming something in the middle of while I was trying to do class, and so I was losing internet last year. Okay, at least then, Dan, very good. At least I know you watched the whole thing. All right, so in Faraday's law, right, it's this is one of the trickier topics that we've done, and part of it has to do with directions, keeping directions straight. Now, if you go on the internet and you're looking for Faraday's law, you'll sometimes see Faraday's law written as, you'll see this for Faraday's law. Right, so for those of you who know vector calculus, this is the differential form of it. This is the integral form of it. So we're not going to use this form, but just know that if you're looking around and you see this thing, the curl of E is minus dB dt, that's also Faraday's law. Okay, so what we're going to do, so in Faraday's law, we're going to use this to find induced, what Faraday's law tells us is that changing magnetic fields will induce electric fields. So you can actually generate an electric field by changing the magnetic flux. So phi B is magnetic flux through some surface. All right, and in the video, and so I'm just trying to decide how much of the video to review. Let's just look at, let's look a quick review of this. So phi B is magnetic flux. And this is, and it has units of Webers, which is a Tesla meter squared. And it is much the same as if you remember what electric flux was. Phi E, electric flux. Right? So electric flux, if I have an electric field E going this way, and I have some surface like this, right? If this has radius r, then and this is a uniform electric field going this way, then phi E through this surface would, if there's an E field going this way, would just be E times pi r squared, where r is the radius of this circle. So that's it. So that's the electric flux through this. Magnetic flux, same thing. So for magnetic flux through this, if I have a B field going this way, phi B is equal to B times pi r squared for this surface. Obviously, if it's a square, it'd be pi times a squared. Or sorry, B times a squared. So it's just the surface area times the magnetic field. Now, of course, if I turn this circle so that it was facing this way and my magnetic field were going like this, then the flux through it is reduced. In this case, if you're looking at the edge of this surface, so you're looking at the edge of the circle, and it makes an angle theta with respect to the direction of the B field, then in this case, phi B is going to be equal to pi r squared times B, so B times area times cos theta. So it gets cut down by a factor of cos theta. And of course, if theta is 0, then cos theta goes to 1, and you get back to just b times pi r squared, right? Yeah, the minus sign in the video, we'll get to that. Yeah, Jade, that's a subtle thing where that minus sign appears. Okay, so let's see. Let's review a little bit more from the video. The next, and then jump in with other questions too. Why isn't it E times 2 pi r? Yeah, Connor. So what you're looking for is the flow through this surface, not, and so 2 pi r is this distance, pi r squared is this surface area. So I want the flow. It's the equivalent of, if you put this in a river and you want to know how much water is, if this were made of screen instead of solid, how many gallons per second are flowing through it would be, the gallons per second per square meter in the river times, so the flow in the river times pi r squared. Does that make sense, Connor? Yeah. So this, yeah, very good. Right. So Connor, you're asking, yeah, but it's ds, so shouldn't it be 2 pi r? Yeah, this, we're looking at the right-hand side right now. So in Faraday's law, you've got integral of E dot ds is minus d phi b dt. And then we're sort of breaking this into pieces. And right now we're just looking at, well, what is the right side of this is the time rate of change of magnetic flux. What is magnetic flux? So we're breaking it into pieces and we're just looking at the definition of magnetic flux for now. And then we'll look at the time rate of change of magnetic flux. And then we'll say, oh, this has to be equal to this thing. And then we'll look at that. Okay. What else? Okay. So then in the video, there are a couple examples. One is, I don't know, this one, it's not too complicated, but you got to think about it a little bit. We do an example where we find the rate of change of magnetic flux if we had, let's see, if we, you can skip some of that. Yeah, a lot of that's in there. So yeah, so let's look at if we had a magnetic field B going this way, and this thing we're turning at 1 revolution per second. Well, we know the magnetic flux through this, when this, so we're looking at the edge of this thing here. This thing has an area of pi r squared, and there's a magnetic flux B. And at this instant, and this thing is turning this way. And at this instant, it's making some angle theta with respect to the B field direction. And so phi B is going to be equal to B times pi r squared times cos theta. Now we know from Faraday's law, we don't even quite know what Faraday's law is yet, but we're just investigating this one piece of it. This thing, whatever that is equal to minus the time rate of change of the magnetic flux through a surface. So we're just investigating, well, what's a case where we could get a magnetic flux changing through a surface? And this would be one way to do it. Because at this instant, the flux through this thing is B times pi r squared. At this, as this thing turns, at this instant, the flux through this surface is nothing because B is going that way. And, forget about this edge, right? It's a circle. And so at this instant, the flux is nothing. And then here, there's actually, if this is the positive normal, when it turns like this, now there's negative flux going through it. And now it's going to go back. Now there's 0 flux going through it. And now there's some positive flux And now the flux is back to a maximum again. So the amount of flux going through this is going to be maximum, then down to 0, then negative and negative maximum, back to 0. And now it's going to increase and go back to what it was. So the flux is, you can get the idea, it's going to have this oscillation to it. And this is phi b as a function of theta. And d phi b dt is going to be d phi b d theta times d theta dt, right, from the chain rule. All right, so this will be equal to minus b pi r squared sine theta, that's d phi b d theta times d theta dt, right? And then this is just the speed at which you're turning the thing. D theta dt is how many, the rate at which theta changes per time. And so 1 revolution per second, that you just have to know, you have to be given, somebody has to tell you how fast am I turning this thing. If it's 1 revolution per second, then this would be 2 pi per second. Okay, so think about this so far, this little example to try to understand how you can get time rates of change of flux through a surface. Right? There's other ways you can get the flux through a surface to change too. This is just one way to do it. You sure? No questions so far? Okay. So other ways you could do this. You could also, I could leave this thing fixed. I could just have it in place here, and I could make B be a function of time, right? Maybe the B field is getting stronger and weaker over time. That would also change the amount of flux through this surface over time. I could also, if this loop were made out of wire, I could squash the wire as a function of time. And if the edge was made out of wire, I could squeeze it as a function of time, and therefore its surface area would be changing over time, and therefore the flux through it would change over time. All those are different ways I could do it. I could also, in this other example that was in the video, I could also say there's just some region which has a B field. Let's say I have a B field coming out of the page in this area, right? So the dots mean the B field is coming toward you. And I could have a loop of wire. Say it's a square, side A, moving with velocity V. And then the flux through this will change as a function of time. The flux at this instant is 0 because the B field, there's no B field coming through it. But then later, the loop is here, moving this way. And so now the flux through it is changing as it's entering, here we go, right? As this is entering the region of B field, it's a little distracting. As it's entering the region of B field, the flux through it is increasing. And then after a while, it's completely inside, still moving that way. And now the flux through it is not changing. There's flux through it, but the flux through it is not changing. And later, the flux through it is decreasing when it's moving out this way. And then later still, the flux through it is constant and 0. Now, one of the things to be very careful about in Faraday's law is it tells us that this quantity, which we don't even know what it is, but clearly it's related to generating an electric field, is minus d phi b dt. So this quantity, which we'll learn later, is called EMF, which has to do with the induced electric field, or the electric field created by changing magnetic fields. Has to do with the time rate of change of magnetic flux through a surface. This is a very important thing to grasp. It is not, Faraday's law does not care about the amount of magnetic flux through a surface. It cares about the rate of change of the flux, not the amount, the rate of change only. Right? So the analogy that I don't know, that I always give, if you want to like, probably this is the same analogy I use in the video because I'm a creature of habit, but right, the force of a seatbelt on your shoulder has nothing to do with how fast you're going. It has, yeah, in this case, yeah, the B field is constant, Gavin. So the force of a seatbelt on your shoulder has nothing to do with how fast you're going. It has to do with the rate of change of your speed. So we only care about the rate of change of the flux through a surface. So in terms of Faraday's law, when the loop is here or here, exactly the same. Because here there's no flux through the thing and it's not changing because as it moves a little, it's still zero. And here there's a lot of flux maybe going through this, depending on how strong this B field is. But in terms of Faraday's law, this is still zero. It doesn't matter how much flux is going through something. What only matters, the only thing that matters is how fast the flux is changing. Right? Okay. So think about questions so far on what we've reviewed up to the point that we're reviewing. Does changing two quantities, the orientation, surface area, strength of the B field, simultaneously necessarily increase the flux? No. So Connor, it's a good question. It might not. Like maybe this B field is going up and down over time, and then, but also this thing is leaving, and so you would have to include all the different effects. Right? If there could be more than one thing going on at once. Right? So, and you would have to include all of those different things. So in this case, if this B field is constant, the flux coming out through this surface is decreasing because the amount of the length of this, the area of this that's inside the B field is shrinking over time. Yeah, so like if it was leaving and the B field was going up, the flux wouldn't change too much. Yep, you could imagine you might be able to cook up a system in which the speed at which this thing were leaving, you could compensate by increasing the magnetic field as a function of time while this is leaving to keep the flux through it constant as it were leaving. Yep, you could do that. And then we would say, oh, with that case, now Faraday's law sees this right side as zero when you're here, but it would see it as non-zero here because the B field's maybe the B field's increasing still, or maybe you could just start dialing it up only when it starts leaving, right? So the point is, what we're always going to be looking for in Faraday's law is the rate of change of flux. We'll often find the flux as a function of time, but only for the purpose of taking its derivative so that we can find this quantity, right? Okay, good. So any questions on this left side of the right side of Faraday's law, d phi b dt? And in the video, we do this example properly and say, and relate the speed of this object, of this rectangular loop to how fast the flux is decreasing. Right. But any questions on this before we go on? Then we'll look at the left side. Okay. So the first thing in looking at the left side is to remember Ampere's law. I can bring back some flashbacks from problem 4 from the exam. So now we're going to get into looking a little more at the details of this. That circle on the integral is a reminder that we have to integrate over a closed loop. So according to Faraday's law, this left side right? So if we look at the left side of this tells us we want to integrate E dot ds around a closed loop. Well, remember what you did with Ampere's law, right? We had this for Ampere's law, right? You had integral of B dot ds is mu naught times I enclosed. And so if I had, for example, I might as well, by way of review, to just, I guess it's review for the final now. If you had a cylinder of inner radius A and outer radius B carrying a current I like that, what I know is that for any loop I draw, any loop, the integral of B dot ds around the loop is equal to mu naught times the current enclosed by the loop. And so if I draw this as a loop at radius r that's outside, what I know is that, and here, remember with Ampere's law, you had to be very careful with choosing directions. If I choose ds to be positive this way, around this loop, then the normal to this surface made by this blue loop is out of the page. You got to be consistent. So if ds goes this way, normal to that surface goes up, comes toward you out of the page. So in this problem, then what we said is, okay, B is the same everywhere on this loop and will point around this way. And so B times 2 pi r is mu naught times how much current is breaking through this surface is I, because all of it is breaking through the surface because it's all inside. So it's mu naught I. And then you could divide and say B is mu naught I over 2 pi r. So in Faraday's law, we have the same thing, except now on the left side, we're going to be calculating E dot ds around a closed loop. And again, we have to be careful about choosing the direction of ds and be consistent when we choose the normal, all right? So if I have an electric field, let's suppose, we don't know how we're generating an electric field that does this yet, but suppose I had an electric field that went around this way. So at this spot, the E field goes that way. Over here, the E field goes this way. Here, the E field goes that way. If I could do that, if I chose ds to be this way, if I choose ds vector to go around that way, integral of E dot ds is clearly going to be a positive number if I integrate E dot ds around that closed loop. Okay, and so now what we can see is sort of what Faraday's law is apparently telling us is that the integral of E dot ds around this closed loop is minus d phi b dt. But now we got to be careful. What this says is this is around a closed loop. And this is rate of change of flux through surface. And here is the critical point. This loop and this surface have to be, they are partnered. As soon as you choose a loop, there is a surface that corresponds to that loop. So if this is my loop, then this is my surface. And if I choose ds, the positive direction around the loop, to be this way, the positive normal to this surface is out of the page. You got to choose them consistently, all right? Okay, so let me stop and see if you have questions so far, and then we're going to do an example. Okay, so one last thing then, actually, before we do just a straightforward example, let's look at how this generates an electric field. So if I have let's say I have a magnetic field coming out of the page. So if I have a magnetic field coming out of the page in this region, If I have a magnetic field coming out of the page, and let's suppose that B is getting stronger over time. So, dB dt is greater than 0. The B field is coming toward you, and it's getting stronger and stronger every second. Okay, now let's be careful with the signs and see what this says. So according to this, if I make, so like Ampere's law, Faraday's law is always true. For any loop and surface pair you choose, Faraday's law will always be true. So according to Faraday's law, let's just, let me choose a loop and a surface. So this orange dotted line is my loop, and that automatically chooses my surface for me. This blue region is my surface. And now here's where we got to be careful about the signs. I'm going to choose positive ds vector to go around this way. If I have a line, I'm going to integrate around the line. I got to choose which direction ds points. Is it that way, or is ds point, the other way? Choose either one you want. They're both fine. So I'll just choose ds to be going in this orientation. All right. Hang on, this doesn't, I just need to put a dotted line because sometimes it's hard to see when somebody has typed a new chat question. Okay, so if ds goes this way, if I've chosen that, then this blue surface, obviously the normal to that blue surface is either out of the page or into the page, but I don't get to choose which anymore because I already chose ds to go that way. And that fixed my choice for the normal for this surface to be out by the right-hand rule. All right, so let's look at the signs in Faraday's law and understand how this would work. So if B is getting stronger over time, so B, that means dB dt is greater than 0, which means the flux, and now the B field is going out, and this is where you really have to use the sign carefully. The flux is going out of the page, and the normal to this surface is also out of the page. So phi B is positive. Phi B, if we chose ds to go around this way, then the positive normal would be in, and a B field coming out would be negative flux. So that's a very important thing about the sign, to keep track of that. We chose ds to be positive that way, so positive normal is out, and the B field is coming out also. So the flux is positive. And we also know, since B is getting stronger as a function of time, d phi B dt is positive. All right. So questions so far? All right, if d phi B dt is positive, then obviously negative d phi B dt is negative. Okay. And that tells us then that integral of E dot ds is also negative. So that tells us that there is an induced electric field so if E dot ds has to be negative and ds points around this way, that means there must be an induced electric field that's going around this way. So the amazing thing about this, and while we're going through all these signs, we don't want to lose track of just how important this Faraday's equation or Faraday's law is for our modern functioning world. Is that this says that in this region of space, if you just have a B field and you dial up the strength, you will generate an electric field that goes this way. Right? And now you can imagine, I could put a wire here. I can put a wire like that, and I could put a resistor here, maybe a light bulb, a resistor in the form of a light bulb, and this thing will light up just by adjusting the strength of the magnetic field is a function of time. And so Faraday's law is what lets you generate electricity, right? And as I know I say in the video, right, before my great-grandfather, this was not known. And so, right, nobody ever uncovers ancient electric generators, right? Prior to, around my great-grandfather's time, Faraday's law was unknown. You cannot make electricity from anything, right? So there's exceptions, like solar cells do not generate electricity through Faraday's law, but everything else, coal power, nuclear power, hydroelectric power, wind power, they all generate electricity from Faraday's law. Right? In the case of a windmill, right? In the case of a windmill, you have essentially a big coil. Somewhere buried inside it, there's a gigantic coil, and there is a permanent magnet. And this is one of the reasons for huge worldwide demand of I think it's indium is one of them, for high power magnets, because you need them to generate electricity. And for some reason I'm blanking. Somebody else type in. I don't know how I've lost the name. The other elements. Yeah, sorry, I said windmill. I meant, neodymium. Thank you. So all the rare earth elements that are used to make strong electric fields. I said windmill. I meant wind turbine. Being sloppy. Thank you. So if I have a coil of wire and I have permanent fixed magnets and a B field is going this way, then if I grab hold of this thing and I force it to turn, so here's my loop of wire and there's a B field going across it, and I force it to turn in the presence of a magnetic field, the magnetic field flux through it as a function of time is changing, because, right, like that first example we did, there's a lot of flux through it now, and now there's none, and now there's negative flux, and now none, and now positive again. And so as that's changing, that generates an electric field through the loops of this wire and generates a current. And so it's not really much more complicated than that. Hydropower is the same thing. It's just, instead of using the wind to spin a turbine, which is attached to this coil of wire, you use the power of water dropping over some edge to force, use the kinetic energy of the water to force a coil of wire to spin in the presence of a magnetic field. With nuclear power, you heat up water and use the steam from the heated water to spin turbines that are in the presence of magnetic fields. Coal power, you burn coal to make steam to turn the turbine in the presence of magnetic fields. But in all cases, you generate energy. You convert energy from either wind or falling water or burning coal or nuclear fission into something that spins this in the presence of a B field. All right. And without Faraday's law, you don't make electricity. It's the first law we've seen. Everything we've seen up to now is either about electric fields or about magnetic fields. Faraday's law is the law that the first thing we've seen that ties the two together. Right? There's a reason the course is called electromagnetism. There's not one course on electricity and one course in magnetism. Right? But okay. So think about questions so far, and then we'll do a specific example of this. The steam that comes out of the nuclear, the cooling structures is boiled water. Yeah, there's, I guess you'll learn this when you do more thermodynamics, right? You would wish that all the energy that you would produce from nuclear fission, you'd hope that all that thermal energy would just go into driving this thing to turn. But the second law of thermodynamics will tell you that if you're living in an environment that's at this temperature and you heat up steam to here, you're not going to be able to convert all of this excess thermal energy. You can't convert it all into mechanical energy to spin this. You will always have waste heat, and you can calculate the amount of waste heat that you'll have to throw back out into the environment. So the short answer is yes. The steam is from boiled water, and then unfortunately the water is warmer than it was, and so you often, in order to cool it, they often have to dump the water back into a river or something, because you got to bring things back down to temperature. Now, you can't just keep storing the thermal energy. So there's always, all of these things have waste thermal. If you use a temperature gradient to produce mechanical work, there will always be waste energy. Not so in the case, obviously, of a wind turbine, because right, you're not using a thermal gradient. You're just using the wind to make this spin.
Would you say that as in you're using the wind for mechanical energy rather than thermal energy?
Sorry, go ahead. What did you say?
You're using the wind to produce mechanical energy, not thermal energy.
You're
Producing the electricity through a mechanical process, not a thermal process.
That's right. Yes, exactly. So in the case of hydropower, there's no waste heat. And in the case of wind turbines, there's no waste heat. But in nuclear or coal, there's always waste heat, because you heat something higher than the temperature of the environment, and then you use that thermal gradient to produce mechanical work. Going to suck up all the wind. I know, Connor, you say that as a joke, but you can Google search it. There was actually some of our illustrious elected officials in Congress actually expressed concern that if you put up too many windmills, you would somehow like deplete the wind, and the wind is needed for things like, crops and seeding things, and so there was actually some of our elected officials were concerned about that. And
that's an argument for solar, but not for wind.
Yeah, there was some concern that I hope they were able to assuage. That's there was concern, but that person needed to maybe do a little what's called order of magnitude calculation and estimate the fraction of the Earth's surface that would be covered with windmills. All right. That needs to take. Hang on. I'm just looking through questions. Okay. All right. So questions so far before we go on, and we're going to do a couple calculations of this. Okay. And the reason, by the way, that this is a coil is not just a single loop of wire, it's just efficiency, right? You don't want, if you're going to build this whole thing, you don't want just a single loop of wire. I guess you could, in principle, make some gigantic loop of wire and huge magnets, but why would you do that? Instead, you would make, this coil of, I don't know, on the order of, say, 10,000 turns. And then that way you can keep the whole thing smaller. And there's the flux goes through each one. So a loop coil of 10,000 turns will act like 10,000 single loops of wire stacked next to each other. And there's change in flux through each one. And the more turns you have, the harder it's actually going to be to twist this thing in the presence of a magnetic field. And we'll talk more about that later, right? So you don't get energy for free. So the more turns are on this, the harder it is to twist it. And I'm sure it's it's an engineering issue between how fast the turbine spins, how fast you want this to spin, and how much force you want to be on the structure inside while you're trying to turn this thing in a magnetic field.
I wish I could get my old tech teacher here. He built wind turbines for GE, and that's what he did for a living before he was a teacher.
Oh, really? Yeah, GE is now become a major player in wind turbines.
Yeah.
Okay. let's try to do a specific example of this. Oh yeah, so one last thing before we do an example. This, and somebody, I can't remember who now, had asked about this minus sign, right? So this is, we're not deriving this. This is an experimentally verified fact, but this minus sign, when you see in your book something called Lenz's law, don't get freaked out like that there's some new thing on top of Faraday's law. It's just that this minus sign goes under there's a name associated with the fact that there's a minus sign in that. You don't really need to worry about that. This is Faraday's law. And but there is a trick to getting the directions correct that I'll show you as we go along, right? But this minus sign that appears, because we find it appears in nature. And I mean, there are other reasons for this, but we can't get into for now, but that goes into the name, under the name of Lenz's law. All right, so let's think about questions for a second, and then we'll do a couple examples. Okay. So let's look first at, let's suppose we have a region. Actually, yeah, we'll do this this one might be too easy an example, but we'll do this one first and kind of quickly, and then we'll do another one. Let's suppose I have, a battery wired here. And let's say this, so we have a square of wire, 2 meters on a side. And let's suppose that there's a B field coming out of the page, but only in this top half only in this region. There's no B field here. Right, so there's a B field up here, but not below the red dotted line. All right. And let's suppose that this B field strength is changing as a function of time. So let's say B outward is equal to 0.42 minus 0.87 T Tesla. All right, so just think about that for a second. So at time equals 0, the outward B field is 0.42 Tesla. And then, I don't know, somewhere around a half a second, the B field is 0. And then as time continues, then the B field points inward, because obviously, after 5 seconds, this term is larger than that one. So now the outward B field is negative, meaning it's inward. Right? So we have B field that's changing as a function of time. Okay, so B field's changing as a function of time. Let's find the induced EMF. So this quantity, integral of E dot ds around the loop, is called EMF. It's an historical name, electromotive force. It's also often written as script E. It's not the same as voltage, but we'll get into the subtleties of it later. Let's not worry about that for now. So the integral of E dot ds around this whole closed loop is what the EMF is. This is not electric field. It's integral of E dot ds. All right. EMF reader define. Yes, Dan, it probably is. An EMF reader to find spirits. I'm not familiar. I think that's next chapter. But okay, so good. So let's calculate this, and this is not going to be mathematically very complicated to do, right? We're going to find that phi b is equal to, right? We need B times area. So before we know from Faraday's law that the EMF is minus d phi b dt. So all I did there was I just stopped writing that and I just wrote this as EMF script E. So to find the EMF, induced around this loop, I'm going to need to find the time rate of change of the flux through it. So even though what we really want is the time rate of change of flux, what I need to do is find the flux through the loop as a function of time and then take its derivative. All right, so phi b of t is going to be 1/2. So I basically just need b times area. And I'll do 1/2. The area of this thing is 4 square meters, and I'll do a half because only half of it's in the B field. Half times 4 meters squared times the B field is 0.42 minus, 0.87 t Tesla. All right, so that's phi b as a function of time. All right. All right, so everyone okay? Yeah, so Brandon, we'll get to the directions in a second. All right, so other questions so far? Okay, so this is phi b as a function of time, which makes it easy for us to find d phi b dt. So that's going to give us a 2. This goes away when I take the derivative. And so I just have the time derivative of this, which is minus 0.87 Tesla per second. And so d phi b dt is going to be equal to just, if you do this out, you'll get minus 1.74 Webers, Tesla meters squared per second, right? Which is nothing, just, it's basically, it's 2 times that. Right? So d phi b dt is minus 1.74 Webers per second. And I sort of shortcutted a little bit there. I assumed, in fact, right, should have been careful here. I said that phi b is this quantity, which at time equals 0 is positive. So that I'm assuming that the normal to this green surrounded surface is out, which is fine to do, but that means I have to choose ds vector now to go this way.
Where did the 1/2 come from? You might have said it. I might have missed it, but sorry.
Oh, yeah. The 1/2 came because only half of this square has flux going through it.
Oh, okay. Okay. Thank you.
Okay, what else? Okay, so d phi b dt is minus 1.74 Webers per second. And so
Professor, there's a question in the chat that I also kind of want to know. How did you get 1.74?
Oh, yeah. So just it
is just running the function?
Yeah, well, just if you take the time derivative of this, so this is phi b, so d phi b dt will be equal to, let's just do that. So we'll have a 2 times the time derivative of this is 0.87 Tesla per second. Right, so just, minus. Right, so I've got 0.87 t. I need to take the time derivative, which
yeah, if you took the derivative of that, you'd get 0.87, and then 2 times negative 0.87 is going to be 1.74.
Yep.
And the reason you can, okay. Now, why would you only take the derivative of that side of the equation?
Because, right, if you do this, if you look at this, phi b as a function of time is equal to some number, right? Whatever it's, I guess 0.84. If I'm doing right, is 0.84 minus 0.87 t. What's the time derivative of this function? I don't care about that when I take the derivative.
Okay.
Right.
But you're still multiplying by 2, which is where I'm still getting lost.
Yeah, because the function, right, once I multiply this in, phi b is, 0.84 minus, oh yeah, you're right. If I'm going to do it that way, yeah, I'm being too quick. I'm skipping too many steps.
Yeah, it's because you can pull the 2 out in front of the...
Right, so really phi b is equal to 0.84 minus 1.74 T Tesla meters squared. Right. So just multiply this in both cases.
So you distribute, and then when you take the derivative, you're
Yeah,
gonna
yeah, and I'm sorry, I shouldn't have just written it this way and included it here and not included it there, and so I just made it more confusing.
Okay, yeah, now that actually makes sense. Thank
Right.
you.
So fine, when I take the derivative, that vanishes, and that leaves me with this. Right? Yes, Dan, exactly. That's what Dan is saying is what I should have done. It often happens. I skip steps and then it winds up being slower. I should have just done it this way from the start. So when I take the time derivative of this, I get this many Webers per second, Tesla meters squared per second for d phi b dt, which means, well, the first thing to notice in this is notice that the 0.42 doesn't make any difference. This, you could change this number to be something else. It has nothing to do with the problem. It disappears because we don't care about the amount of flux through this square. We only care about its rate of change. And this does not have any influence on the rate of change, right? Okay, good. So this gives us d phi b dt. Now minus d phi b dt is equal to 1.74 Webers per second, obviously. So, and that tells me that E is equal to 1.74 volts, right? So there's 1.74, and actually, the way I did this example, I was going to do a slightly more complicated example, but let's skip that for now. So forget about that battery. Just have a loop of wire. So E is 1.74 volts, and now we got to be careful about the direction. This says that the integral of E dot ds around this closed loop is 1.74 volts, positive 1.74 volts. And that means since ds goes this way, E, the induced E, must also go this direction. So if you put an ammeter here, you would find that current is flowing in this wire this way. And if you put a little light bulb here or something that used electrical energy, it would light up and current would flow this way through it. Right? Yeah. Does all this mean that the direction of E flow is dependent upon whether the magnetic flux is increasing or decreasing? Exactly right, Connor. Yep, very good. So in this case, if the B field is pointing out and shrinking, we found that the electric field, the EMF is generated, will generate a current that goes counterclockwise, looking down on it as we are. And the first thing, and this I want you to do on your own as an exercise, if I had switched ds and decided ds was positive in the other direction, then positive normal would be in and the magnetic flux would be negative. It would be negative, but getting less negative over time. And you could go through all the signs and you would still get the induced EMF goes counterclockwise. Because you'd switch directions in two places and you'd have the induced EMF going the same way, which it has to, because the direction of an induced current when you change a magnetic field can't depend on like our thinking about whether we're thinking about this is the positive direction or this is the positive direction, right? So the actual direction of the induced EMF won't change if I do choose ds to go the other way. But Connor, your question is important and slightly different. Let's keep ds going this way as I've drawn, and positive normal is out of the page. And let's suppose that instead the B field were pointing outward, but we're increasing as a function of time. So if that were a plus, so it's 0.42 plus 0.87 t time Tesla coming out. Now the B field is coming out and getting stronger as a function of time. Now what we would find is since the positive normal is out, only because I chose ds to go around that way, positive normal is out, So the flux is positive and increasing. So that means we would get d phi b dt to be a positive number. And then negative d phi b dt would be a negative number. And therefore, the induced EMF would be a negative quantity. So if the B field were pointing out and getting stronger over time, the induced current would be this way. If it's going out and pointing inward more as a function of time, the induced current goes that way. Right? Does that answer your question, Connor? Or think about this stuff with directions is not easy. So think about questions for a minute. Yes, so Connor, exactly right. When spinning, and I was actually going to talk about this. So if I have a B field going like this, and I turn this thing, in fact, let's just do that example. Let's say I have a B field pointing this way, and I turn, and this thing is spinning like this, right? So right, I have a wind turbine or something forcing this to turn this way, but I have a fixed B field going like that. At this moment, the flux through it is large. Let's say this is positive orientation around the loop, which means this way is positive normal. So at this moment, the flux through this surface is large and positive, but it's shrinking as this thing turns that way. So if the flux through this is shrinking, d phi b, so the flux through this is getting smaller, d phi b dt is a negative quantity. If this is positive normal and this is normal around, this is positive orientation around. So the flux through this is shrinking. So d phi b dt is negative. Negative d phi b dt then has to be positive, obviously, which means induced EMF is positive, which means there will be a current that goes this way while this is shrinking. And now the flux is zero. And now this is an interesting spot here. The flux is zero. So it was positive flux, and then it was falling down, and then it hit zero. And then you think, ooh, what about now when it goes negative? Does it flop? Does the direction of the current switch? And it doesn't, because it goes from positive to zero to negative. So it just keeps going down. It passed zero, but it's still d phi b dt is still negative. So now there's negative flux, and it's getting more and more negative. And so the induced current is still it's hard to track it, but it'll still be going this sense as it goes around. It'll still be going like this as it goes this way. It's still going to be going this way. But now something interesting happens. Once it hits here, we've gotten to maximum negative current, or maximum negative flux, rather. And now the flux through it starts to get less and less negative. So this is where you got to think about this for a second. As I turn it here, the flux is negative and large while the B field's going that way. But as I turn it, now the flux, here's zero, the flux is negative and large. It's going back up towards zero, which means now d phi b dt is positive, which means negative d phi b d is negative, which means the EMF induced is the other way. And so the current in this thing will go one way, and then it'll get smaller, and but it'll still be going the same way. It'll still be going the same way. And now it'll hit, I'm sorry, actually the induced EMF will be small and negative here. And then it's going to switch directions as soon as this passes this point. And now the current will go the other way. So in fact, wind turbines and anything that turns a coil in a magnetic field, which is most things that generate power, they they naturally generate alternating current, right? And in fact, they because of the facing area is a sine, they actually naturally generate nice sine wave AC current. And then if you want DC, then there's engineering that's involved in generating DC, switching AC current to DC. Okay, so Connor, does that answer what you were asking? Okay, and I mean, I'm simplifying this quite a bit because it's not really so easy, right? So you have some wind turbine, and you have a coil somewhere in it, and then this thing, right? So you've got your windmill, which somehow became detached from the rest of it. So you've got the actual turbine. Now the problem is that, right, we're not going to get into the details of this, but there's a lot of electrical engineering that goes into this because the speed that this thing turns, is not necessarily, yes, thank you, Eric, thank you. The speed that this turns will change the speed, obviously, that this turns, right? This is physically geared to this. And so the AC current that comes out of this is not 60 hertz unless this thing is geared to turn at exactly that speed. And then when the wind blows harder and this changes speed, this changes speed. And so the frequency of your AC current that this generates is going to change. And so there's a lot of transformers that are used to convert power at one frequency to a different frequency. And if you have a field of these, every single one of them is going to be turning at slightly different speed. And so the EMF that it generates, right, this time is going, this period between peaks is going to be different for every single windmill, even in a group of them. But you're going to have to combine the energy output from all of them into something that can be then shipped down the transmission lines. Right? So it's the engineering of it's complicated, but the basic principle of it is just Faraday's law. Right? Okay, so think about other questions on this example. We kind of drifted from this example into something else, but I don't want to block off questions from that. I'm looking at back to see if there were. Jeff, are you okay now on the 1.74? Okay. All right, other questions on this one? And then we're going to do another example. Okay. So let's look at, let's take a large loop. So this is a cooler example. I didn't want to do this one first, but I like this example. So we're going to have a large loop with a changing current in it. And we're going to say that I at 0 is 200 amps. And then I at 1 second is minus 200 amps. All right. So we're just going to have and we're going to say it continues like this. And so you can see what's happening, right? The current here's 0, it's 200 amps, and then at 1 second, and it's going to continue in that same linear path. It was 200 amps at 0, so it must have been 0 at half a second. And then at 1 second, it was minus 200 amps. I guess at 2 seconds, it'd be minus 600 amps. So it's dropping or increasing in the backwards direction at 400 amps per second, right? So we have a changing current through this wire. And then we've got a small loop at the center. And we're going to say the area of this is 2 centimeters squared. And we're going to say this radius, the distance of the radius of the large loop is 1 meter. All right. So our goal is to find E induced in the small loop. All right. So our goal is to find the induced E in the small loop. So first, let's just understand what's happening before we just dive into formulas. So we have a current going like this in a loop, in this green loop, which means, you know, from last chapter, there is a B field that comes out of the page everywhere in here. But since the current in this loop is changing as a function of time, the B field in here, is also changing as a function of time. Okay, if the B field in this region is changing over time because the current's changing, that means the flux through this loop, this inner wire, is also changing as a function of time, which means there's an induced EMF around it. All right, so let's figure this out. And the first thing we're going to do, if you remember when we calculated the B field inside, you know, if you have a ring of so mu naught I over 2R, the B field inside at the center of a loop of wire, we actually only ever calculated the B field at the center. So technically, to find the flux through this, you would have to find the B field as a function of position, because the B field here is not really the same as the B field there. But we're going to assume that this loop is small enough, and it's not drawn to scale, right? If this was a meter, 2 centimeter square thing is going to be, you know, like this. And so we're going to assume that this inner loop is small enough that we're not going to worry about the fact that the B field here is not quite the same as the B field at the center. We're just going to assume a constant B field throughout this whole surface so that we can find flux more easily. Because it's very complicated actually to find the B field slightly off center. You have to use approximation methods to do it. So we're not going to do that. Okay, and I'm going to choose, and this is a free choice, I'm going to choose ds vector to go around that way. But before we actually get into doing the calculation, think about questions on this for a second. So what we have so far. Okay, so I know the B field at the center of the loop, so B at center of inner loop is mu naught I, meaning whatever this current is here is a function of time, mu naught I over 2R. R is 1 meter. So this is B at center of loop over 2, okay? All right, so B is a function of time is going to be equal to mu naught I of t over 2. And so that's going to be mu naught over 2. And now I need I as a function of time. The current in this loop as a function of time is 200 minus 400 t Tesla. All right. Right. So that's just, I just said, well, it was 200 at 0 minus 200 at 1. So I is a function of time. It's mu naught I of t. I of t is just 200 minus 400 t. Right? Because it shifts by 400 amps every second. Okay, so then the flux through the inner loop, phi of t through inner loop, so the flux through that inner loop is going to be 2 times 10 to the minus 4 meters squared, right? This is right? We just need B times area. So that's the area. 2 centimeters is 2 10 to the minus 4. 2 centimeters squared is 2 10 to the minus 4 meters squared times this thing. Right? And if you just do the arithmetic out, you should get 0.02 mu naught minus 0.04 mu naught T Webers, right? So nothing really happened except I just picked up what we did from last chapter of what the B field is at the center of a loop, and then said, all right, so the flux through this inner loop is going to be that B field times the area of the loop. And the B field is a function of time because current is a function of time. So this is B as a function of time at the location of the loop. And then that times the area of this little loop is the flux through this loop as a function of time. And now I can take the time derivative of this to find the induced EMF. So d phi b dt, I just have to take the derivative of this, which gives me minus, right? So easy to take the time derivative of that. This goes away, and that gives me minus 0.04 mu naught Webers per second. And so that tells me the induced EMF. So the EMF, if you just plug into this thing, you'll have induced EMF. I need minus of this, so I'll get 5.04 times 10 to the minus 8 volts. So I just got that by plugging into this, plugging in for mu naught. So it's 5 10 to the minus 8 volts. Yeah, is there no unit symbol for Webers? So not to confuse with watts. Yeah, there's not. It's just sometimes I try to sometimes write out Webers so you don't mix it out. The 200 minus 400 T, this part, is that what you're asking, Evan?
Yeah, if you could just go over how you got the 400 in particular, I didn't catch.
Yeah, so I mean, you kind of got, I'm sure there's some fancy formal, y equals mx plus b sort of thing to figure this out. But think of a function. I tell you the function at 0, it's 200. And then at 1, it's minus 200. So what's the function? It's 200, its slope is 400 per second, 400 amps per second, because it dropped from plus 200 to minus 200 in 1 second.
Oh, okay. Okay. And you just
so-
okay, I see that.
Yeah.
Okay.
So I wrote it as 200 minus 400 T.
And you just found the slope of that line, essentially. You found an equation that represents that line.
Yep.
Okay. Okay. I see that.
That's what I need. If I want phi, what I really want is d phi b dt. But to get that, I'm going to need phi of t. And to get phi of t, I need b of t. And
Right.
And to get b of t, I need I of t. And so we sort of worked our way forward to get this by starting with I as a function of time.
So we recalled from the previous unit that mu naught I over 2R is the center of the loop. And then what did you plug in for R though? Is that what you
I just said in the problem, suppose this is 1 meter. So R just turned into
Oh,
1.
okay. Okay. And then you found the area, and then okay, I see what you did now. Okay, thank you.
Yep. Okay, good. What else?
I had a question. You have it as like 200 minus 400 T. Is it just because it's going from 200 to negative 200, or is it always going to be minus?
Well, no, it wouldn't always. It's just because in this case, the problem says that at time you have a steadily declining current, and all you know is that at time equals, when you started your stopwatch, it was at 200 this way, and 1 second later, it was 200 that way, which means it must have dropped 200, then at a half second, it was 0, and then at 1 second, it was minus 200. Another second later, it's going to be minus 600 because it's dropped. It's going this way. Its rate of change is 400 amps per second this way.
Okay, I just didn't know if it was like the rate of change, but like always minus the rate of change, or if it was that this rate of change is minus.
Oh yeah, right. No, it is not always. It just so happens that in this case, you're given that this is what it happened to be.
Okay, thank you.
Yeah. What else? Other things? Yeah, the 5.04. Thank you, Christina, for answering. Whose question was that? Jeffrey. Yeah, so that just plug in 4 pi 10 to the minus 7 for this, and that'll give you that.
Can you explain how you got phi of t flux through the inner loop again, please?
Oh yeah, so the flux. So if you have a surface of area A and a magnetic field B, going into it, and let's say it's facing it straight, then the phi b through this surface is going to be b times a. So in this case, I said, okay, I know the B field at the location of this loop is mu naught I over 2. So then I put in I. So this is the B field as a function of time where that loop is. So the flux through this is going to be this B field times the area of the loop.
Okay.
Right. And the area of the loop is 2 centimeters squared, which is 2 × 10⁻⁴ meters squared. So just being careful with units. Is that all right?
Yeah, I got it.
Okay, good. All right. So, well, time flies. It's actually 11:50, so we should stop. So go through and, this chapter can be tricky. So start the homework early. And then basically next class, we're just going to do more examples of it, but you'll, so just practice examples between now and Tuesday. Dan, can you ask the TAs to be more specific on grading of exams? What do you mean specific? You mean exams or quizzes? Oh yeah, I listen. Honestly, normally I don't. I did that partly just because I was jotting them down on a sheet of paper, and then I didn't. But if you have a question, you can ask them. The only thing I told them is give plenty of partial credit wherever you can, but they usually do that anyway. But yeah, normally I don't do that with parts, but I don't know, I just happen to. Yeah, Patrick, you can email me, but it's better to come to office hours because otherwise I just get so swamped with emails that I can't always answer them. Let's see, the final, I forget, it's whatever's the official day is decreed by the university is when the final is. I don't know what the grading scale is. Maybe probably by Tuesday, I should have time to look at it. Yeah, Nina, I hope I didn't screw up it's Faraday's law. I forget the chapter number. It's different if you're looking at Survey or looking at the open source book. Answer key to the test should already be posted. Let me know if it isn't there. Okay. Yeah, so for questions, it's better to come to office hours just because also I should have office hours today. They might get cut a little short. But I will, and then it's 1:30 to 2:30. They'll probably get cut a little short today because I have a meeting, but then I can arrange a time to meet with you later. Okay. All right. Bye all.